Okay. In the last class, we discussed about a few simple codes on GPU, right? How can we write a few simple codes by using CUDA? Okay. We executed few programs. In this class, I would like to discuss about okay a few properties of CUDA device. Later, I would like to discuss how to write a few simple programs. Those are a simple dot product of two vectors. And suppose if you want to multiply two matrices, how can you multiply the two matrices by using CUDA? Okay. Before going to proceed further, first I would like to discuss uh, how can we study the properties of any CUDA device. Okay. For that, we can write a very simple program. When we execute that particular program, we'll get some information about that particular one. Here I'm going to execute one program that is CUDA device properties.cpu. CU. When you look at this particular one here, you can see that. Are you able to see this particular program?
Yes, sir.
Yeah. Here there is a function. Okay. CUDA get device count. With the help of this particular one, we can get some information about number of CUDA devices do we have. Suppose when we are using a DZX machine, okay, when we are using DZX machines, we can have number of CUDA devices is at least 4 or 8. Okay, with the help of 4 or 8 devices, we can write efficient programs uh, while performing a particular task, right? That is, if that particular task is highly parallelizable, then we can compute that particular task by using multiple devices. Instead of one device, we can get the we can use multiple devices to solve that particular problem. Okay. Yes, when we executed this particular function, CUDA get device count, that particular count is going to be stored in the variable count. Later, if we print that particular one, we'll get some information on number of devices. Okay. After that, suppose if we want to execute our code by using a particular device, okay. Suppose we got the number of devices is 8. Okay. If number of devices is 8, usually device numbers are from 0, 1, and so on 7. So suppose if you want to execute our program by using particular device 0, then we are going to write CUDA get device of 0. This is the device number. Okay. Are you with me? Or CUDA set device. Okay. We can set that particular one. Did you get my point? Suppose if when we use CUDA set device, we are going to execute our code by using that particular a device. Okay. Next, suppose if you are executing our code by using particular device, we want to know the number of that particular one. We can get it with the help of CUDA get device. With the help of CUDA get device. That is the difference between CUDA get device and CUDA set device. Okay. Suppose if you want to print that particular device number, here we can print it with the help of that particular statement. After that, suppose we want to know the properties of the device. Okay. Then what we have to do is we have to call the function CUDA get device properties. Get device properties of this particular I. Suppose if you want to study the properties of 0, here instead of I, we have to pass 0. If you want to study the properties of 1, instead of I, we have to pass 1. Okay. Then we'll get the properties of that particular GPU card. GPU card. Okay. That is simple structure. In that particular structure, we are going to store the information of that particular card. Okay. Later, when we execute these statements, we'll get that particular name. What is the name of that particular device, GPU card, and clock rate is the frequency. Okay. Based on the particular frequency, then only we can calculate maximum throughput of that particular one, or speed of that particular device. Okay. Device overlap. Okay. What is the, I think you have some idea about device copy overlap. Okay, here idea is very simple. When we look at this particular device copy overlap, Usually, while working with GPUs, we have two machines. That is host machine, and we have a device. We have a device. In this context, suppose if you want to perform any computation on the device, what we have to do? First of all, we have to copy that particular data from host to device. We have to perform that particular copy. Later, we have to execute it by using device. After that, once we execute it, we have to copy back the result from the device to host. We need to perform these three operations. When we look at this particular one, okay, this is a kind of a simple three-stage pipeline, right? What is the first stage? First stage is copy. Second stage is execute. Third stage is copy back. Are you with me? That is similar to the instruction pipeline. When you look at the four-stage pipeline or five-stage pipeline, what are the stages in that particular one? Instruction fetch, instruction decode, okay, operand fetch, execute, write back. These are the stages, right? Just like that. Suppose if you want to perform computation on a particular device, okay, what we have to do? We are going to copy that particular data onto the device. Later, we are going to perform the simple execution. Later, we are copying back that particular result. This is a kind of simple three-stage pipeline. In that context, okay, then we use the concept of pipelining here or not, or whether the particular device supports the concept of pipeline execution or not. If it supports the pipeline execution, what is the meaning of that? Meaning of that is, suppose we have multiple tasks. Suppose there are different tasks, that is task 0, task 1, task 2. There are multiple tasks are there. Okay. We have to execute these three tasks on the device. In that context, we have to copy some data. Okay. Some part of the data, that is P1. We have this is for T1, we need another part of the data, that is P2. For T3, we need another part of data, P3. Suppose if a particular device don't supports the device copy overlap, in that context, what will happen is, okay, uh, all these operations should be serialized, right? What is the meaning of that? For the first task T0, we have to perform copy operation. Later, we had to perform the execute operation. Later, we had to perform copy back operation. After performing copy back, then only we can copy the data of the next thread. Again, copy, execute, and copy back. Okay. This is kind of non-pipelined execution. If it supports the concept of pipeline execution, if first thread, that means if T0, that means task 0 is in execute stage on the device, right? uh, in that context, actually, we can perform the copy operation of task 1, right? Then copy, execute, copy back. This is copy back of task 1. Are you with me? Then we can save that particular copy operation, right? That is a kind of pipeline execution. Usually in olden days, GPU cards don't support that copy overlap. Nowadays, actually, the latest GPUs V100, A100, H100, this supports the concept of device copy overlap. Are you with me? Are you with me? Did you get my point? This is similar to the concept of pipelining. Okay. Next one here, similarly, we can get some information about global memory, constant memory. Constant memory is, suppose sometimes we are going to use read-only memory or read-only data. Okay, we can share that particular data across all the threads. In that context, what can we do is we can push that particular data into the constant memory. If data is in constant memory, okay, read operation takes less time as compared with data which is there in global memory. Next one is multi-processor count. How many multiple processors are there? Okay, how many what is the size of shared memory? That means that memory is shared across all the threads within a block. Okay, Next one is registers per block. How many registers do we have? And warp size. What is the warp size? Warp is group of threads. Okay. Yes, we can get that kind of information when we execute this particular program. Now, what I'm going to do is I'm going to execute this particular simple piece of code. You know how to execute this particular piece of code. What is the command to execute the piece of code? So instead of GCC here, what we have to do? We have to use nvcc device properties.cu minus o device properties.o. This is executable. Once we execute it, actually it generates the executable. After that, we are going to device properties.o. Yeah, now here you can see that. Okay. I'm able to access only one device. Okay. That is why number of devices is one here. Okay. After that, here, what can you see? You can see that device number is 0. Okay. That is name of device is NVIDIA A100 and SXM4 and size of the 40 GB. Okay. Global memory, size of the global memory is 40 GB. After that, here, what can you see? Here, this is the clock rate. Okay. What is the clock rate here? That this is in terms of, can you guess? What is this clock rate? In terms of megahertz or kilohertz? What is that?
Kilohertz.
Yeah, in terms of kilohertz. Okay. If we convert this particular one to megahertz, it is 1410 megahertz. Okay. After that, suppose if we convert this particular one to gigahertz, this is 1.410 gigahertz. Okay. Next one. It supports the concept of copy overlap. That means if one task if we are executing something on the device, we can perform the copy operations. Okay. To or from the particular device. Okay. Then we can save the time. Okay. Next one is kernel execution timeout. Okay. Actually, here we disable that particular one. If you want to enable it, after that, what will happen is sometimes a particular thread enters into the infinite loop or something. In that context, it is going to take it never comes out, right? In that context, what can we do is we can set the kernel execution timeout. When it is enabled, after that particular one is automatically the task is going to be terminated. Next one is size. Total memory is this much amount of memory. This is equal to 40 GB. Constant memory. When you look at the size of the constant memory, this is the memory that is, what is it? It is 64K, 65,536. After that, texture memory. Actually, this is kind of a different memory. Usually, this is used for when you're working with uh, what can I say, image processing applications. Okay. Strictly speaking, I don't have that much idea on that particular texture memory. I never used it. Okay. Honestly speaking, I never used that particular texture memory. Next one is multiprocessor count. When the number of SMs, number of SMs is 108. Okay. Here, in the last class, I gave a little bit overview on this particular SM. A100 number of SMs is 108. After that, when we look at the FPs, floating point units for SM, floating point unit FP32 units. How many FP32 units do you have for SM? How many 30, FP32 32 units do you have per SM? Any guess? Any guess? 64. Number of FP32 units is 64. Okay. Next, in that context, okay, uh, mm, per SM number of FP32, that means floating point, single precision floating points units is 64, and number of SMs is 108. So total number of floating point units per card is 108 times 64. 108 times 64. What is the answer? 108, 108 times 64. Any guess? 6,912. Are you with me? 6,912. That many number of floating point units do we have? Based on that, we can calculate what is that mm, maximum speed of that particular one, right? You can say that it is the throughput of that particular one is um, you can 19.5 teraflops, right? Usually speed is expressed in terms of flops, floating point operations or integer operations per second. Here usually we are going to consider floating point operations. How many 32-bit floating point operations we can perform on it, or single precision floating point operations we can perform on it. Are you with me? Next one, this is the size of the shared memory. Size of the shared memory is it is close to this particular one. This is equal to 48K. And next one is the number of registers per block. How many blocks do we have per SM? How many blocks do you have per SM? Any guess? Four blocks per SM. Four blocks per SM. And registers per block. That is register memory. Register memory is this much. And warp size. That means we can execute 32 threads in one go. Maximum number of threads per block is 1024. Okay. And block dimensions. Okay. Per block, each block is a three-dimensional cube, right? When you look at, we can launch 1024 threads in x-axis, 1024 threads in y-axis, 164 threads in g-axis. When we multiply these three together, it should not exceed 1024. Suppose if we launch 1024 threads in x-axis, then y coordinate value should be 1 and z coordinate value should be 1. Are you with me? Are you with me? Suppose if we want to launch 32 threads in x-axis, then 32 threads in y-axis, 32 are that, and one thread in z-axis. In that context, when we multiply the both, we'll get 1024. You should not cross 1024. That is maximum number of threads per block. Okay, this is the block dimension. Okay, block dimension is a kind of a cube. Okay, so we can launch some number of threads in x-axis, we can launch some number of threads in y-axis, and we can launch some number of threads in z-axis. Similarly, okay, we don't have such kind of limitation on the grid dimensions. Okay, maximum number of blocks in a grid is this many number of blocks in x-axis, this many number of blocks in y-axis, this many number of blocks in z-axis. Okay, next one. Okay, suppose how much amount of maximum amount of memory we can copy from host to the destination. In one go, we can copy this much amount of memory from between host and destinations. Okay, next one is simultaneous operations, whether it is supports the concept of overlapping. Yes, it supports the concept of overlap execution of tasks. It supports the concept of overlap execution of tasks. Next one, mapping host memory into the devices. Yes, it is possible. We can use the concept of host alloc. Okay. There are different computing modes, computing mode 0 and computing mode 1, computing mode 2. Okay. I use those three computing modes. Okay. If you want, you can use whether it supports concurrent kernels. Yes, it supports concurrent kernels. Whether it is integrated GPU or not. Suppose if it is 0, means that it is not integrated. If it is a separate GPU. Integrated means actually in the same CPU and GPU together on particular PCB. In that context, actually, we can say that that is integrated one. Are you with me? Are you with me? Yeah, when we execute this kind of simple program, we can get some idea on what is the architecture of that particular GPU card. Suppose if you want to compute operations on that, we have to write such kind of simple programs, and with the help of those programs, we can get some information about that particular one. Is it clear? Is it
Yes,
clear?
sir.
Okay. Next. Okay. After that, okay. Now I would like to execute. Okay, how to calculate. Actually, when we look at the thread launching configurations, there are many thread launching configurations. Here you can see that. Okay. Here, what can you see? This is block dimensions. This is grid dimensions. Okay. Block is a group of threads. grid is a group of blocks. Okay, in that way you can interpret grid and block. Okay, suppose when you look at this particular block dimensions, if suppose if block dimensions are suppose 2, 1, 1 means that we are going to launch this is the block dimension. That means that we are going to launch 2 threads. We are going to launch 2 threads. Okay. Next one is block dimensions is 2 comma 2. Meaning of that is 2 threads in x-axis and 2 threads in y-axis. This is the meaning of 2 comma 2. Here z value is 1. Suppose we have 3 such type of blocks. Suppose we have 3 such type of blocks. Then in that context, block dimensions are 2, 2, and z-axis value is 3. So total number of threads is, okay, uh, 2 times 2 plus times 3. That is 12. That is 12. Okay. Are you with me? In one block, we can have, how many? 12 threads. Are you with me? Are you able to understand this particular one? Did you get? Yeah, actually, while executing the programs, we are giving this some configuration, right? Here, mm, I would like to give a simple example here. Yeah. Now I would like to give some simple idea on how to compute the global ID for a particular configuration. Okay. I would like to start with 1D grid and 1D block. Then you will get some idea on that particular one. 1D. Yeah, when you look at this particular one, here what can you see? Here we have a function that is compute using GPUs. This function is there. Are you able to see this particular one? Are you able to see that? Hey, I need a reply.
Yes, sir. Asked.
Yeah, right. After that, when by using this particular one here, this is that is the function. With the help of that particular function, what I'm going to do is for a given configuration, here I'm going to calculate global ID. Global ID for 1D grid and 1D block. 1D grid, what is 1D grid? 1D block. Okay, I will explain that particular one. Here I'm going to calculate the global ID with the help of 1D grid and 1D block. Okay, what the meaning of that is grid is 1D grid. What is 1D grid? So in that context, We can have in a grid, we can have blocks in only in x-axis. That is 1D grid. Assume that we have blocks only in x-axis. That is 1D grid. So in that context, what are the grid dimensions? Here grid dimensions, number of blocks is 3. Number of blocks in y direction is 1. Number of blocks in z direction is 1. That is 3, 1, 1. This is uh, grid dimension. After that, okay, 1D block. That means when we look at a block, again we can define number of threads in x-axis and number of threads in y-axis. Suppose here assume that we have 2 threads in x-axis, only 2 threads in x-axis. In that context, what the block is 2 threads in x-axis, only 1 thread in y-axis, 1 thread in z-axis. In that context, this is the thing. 2 threads are here, 2 more threads are here, and 2 more threads are here. Okay. If this is the scenario, this is the blocks, that threads in a block. This is grid. Okay. How the blocks are arranged in a grid. Based on this particular information, we have to calculate global thread ID. Okay. How can we calculate global thread ID? Here, this is the configuration. When you look at this particular the function that is going to execute on GPU, we are passing two parameters. First one is grid. Second one is block. Okay. For grid, we are passing these values. For block, we are passing these values. Okay. With that particular scenario, we are going to calculate global ID for each thread. How can we calculate global ID for each thread based on that? Any guess? Any guess? 1D and 1D, right? That is very easy. 1D grid and 1D block. That means here we'll get the block IDs. Here, what are the block IDs of this particular one? Here only one dimensional grid, right? Here block ID 0, block ID 1, and block ID 2. Next, within a block, we can have threads. This is thread ID 0. This is thread ID 1. Similarly, we can have 0, 1, 0, 1. With the help of this particular information, we can calculate global ID. How can we calculate the global ID with the help of this particular information? So in total, how many threads do we get it with the help of this particular configuration? In total, we will get 6 threads, right? Are you with me? Are you with me? So
Yes,
per
sir.
block, we have 2 threads. How many such type of blocks are there in a grid? 3 blocks. So in total, we have 6 threads. How do we get 6 from this particular example? We look at this particular. Here, block ID is 0. Block ID is 0. 0 times block
Block ID,
dimension. Pardon?
block ID into block dimension plus thread IDs.
Yeah, yes. This block dimension is 2 here. 2. Okay. And thread ID. Here, thread ID is 0. First thread ID is 0. So its value is 0. For the next thread of this particular one. Okay. Instead of 0, we can get 1. In that context, we will get instead of 0, we'll get 1. So for the first block, threads of the first blocks are block 0. Global IDs are 0 and 1. Okay. Now, when we look at the threads of block B1, okay, for block B1, this block ID is 1, and the number of threads per block is 2 plus 0. Then we will get 2. Suppose instead of 0, you will get 1. Then number of threads per block is 3. Are you with me? Are you with me?
Yes, sir.
In that way, we can generate, okay, uh, global IDs. This is the formula to generate the global IDs. If you look at this particular one, okay, block ID x dot x, that means block ID in the x direction. That means here, when we here, what is the configuration? It is here configuration is 311. In that context, block IDs are in x direction 0, 1, and 2. So these were 0, 1, and 2. Next, block dimension. Block dimension here it is, block dimension is in x direction. It is only 2. So with the help of this particular one, we can go to that particular block. After that, with the help of thread IDs within that particular block, when we add both the quantities, we can get the global thread ID. Are you with me? Or is there any difficulty while understanding this particular one? I hope that there is no difficulty, right? Here, I would like to tell one more point. Okay. Yes, actually, these two functions, when we look at this particular logic, this function is going to be executed on the GPU. This function is going to be executed on the GPU. Okay. Here, why we are calling this particular one from this, right? From this particular function. Okay. When you look at this particular written type of this particular, what can we say? We can when we look at the prototype of that particular one here, what here that we added the prefix for this function. We added the prefix global. For the next one, we added the device. Okay, what is the difference between underscore underscore global underscore 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 device underscore underscore? Okay, what is the difference between these two functions? Any idea? Any guess? Suppose if we added the prefix underscore underscore global underscore underscore, means that that particular function is called from the host. That particular function is called from the host and executed on the device. Okay. Next one, when we look at the function get global uh, I, ID, right? Get global ID. That when you look at that particular function is called from the another device function. That particular function is called from the device function and executed on the device. That is why we added the prefix underscore underscore device underscore underscore. Okay. If this particular prefix is there, means that this particular function is called from the another device function and executed on the device. Okay. If we have a prefix underscore underscore global underscore underscore, means that this particular function is going to be executed on the device, and but that function is called from the host function or main function. Okay. Are you with me? Are you with me? Any guess? Okay. I hope that that is clear. After that, here what can you see? I'm going to execute this particular program. Okay. When you look at this particular program, what can you see? I'm going to pass some number as an arguments, right? Here, what can you see here? Yeah. Here, I'm going to pass n as an argument. After that, first three arguments for the grade, and next three arguments for block. Dim3 the data type in CUDA. Okay, that is three-dimensional data type. Dim3 grid is a three-dimensional variable. That means some number in x-axis, some number in y-axis, and some number in z-axis. Okay, similarly, block is a three-dimensional variable. Some number in x-axis, some number in y-axis, some number in z-axis. Okay. After that, what are you going to do? With the help of that particular one, I'm going to pre-fill that particular array. Here, A is an array of so and so size. Size of that array is n. That is the first argument. That is the first argument. Okay. Here, what can you see here? Uh, uh, from this one, here I'm going to call this, but compute using GPUs. Here, what I'm going to compute here, I'm going to initialize this particular array A with the help of these threads. Okay. Yes. Suppose if I pass the grid parameters 4, 1, 1, that means I'm going to launch 4 blocks. After that, I'm going to grid block parameters. Those block parameters are 5, 1, 1. That means number of threads per block is 5. Okay. Yes. If we supply the both for this particular function, that is compute using GPUs, I'm going to initialize this particular array A. That is A of 0 with 0. I'm going to initialize A of 0 to A of 19 with the values that particular global ID. Here global ID is 0. Here global ID is 1. Global ID is 19. Okay. How do I calculate that those values? I'm going to calculate those values by using this particular function, compute using GPUs. When you look at this particular compute using GPUs, here what can you see? Here with the help of this particular one, okay, ID equal to get global ID, okay, 1D grid and 1D block. With the help of that particular one, if it is a configuration is 1D grid and 1D block, with the help of this particular simple formula, we can get the global ID. And C of ID equal to ID. That means we are going to initialize that particular one-dimensional array with the corresponding global ID. Are you with me? Are you with me?
Yes, sir.
Okay. Once we initialize that particular one, here what are you going to do? I'm going to copy back that particular one from device to host. After that, I'm going to calling this particular function display. With the help of this display, we can display all those values on the screen. And all those values are on the screen. Now I'm going to execute it. Now I'm going to execute that particular one. Yeah. What is the command to execute it? NVCC. I don't know. Command is NVCC -o 1D grid 1D block .o. Executed that. After that, I'm going to print those values. Okay. 1D grid 1D block .o. Yeah, size of the array is let us say it is 100. I'm going to create an array of size 100. Here, first three are the grid parameters. Grid parameters, the number of blocks in x-axis is 4. 1D means here remaining things are 1, 1. Next one, mm, number of threads per block. Number of threads per block in x-axis is 6, and remaining parameters are 1, 1. In that context, what are the values do we get it? Do we supposed to get it? Here we are going to launch 4 blocks and 6 thread per block. When we execute it, now you can see the numbers 0 to 23, that is 24. Remaining values are 0. We haven't initialized that particular one. Are you with me? Are you with me?
Yes, sir.
Yeah. If we change that parameters, we can get the proper instead of this particular one. Suppose if we provided mm, 20. Then see, 4 blocks and 20 threads per block. Then we'll get values 0 to 79. Okay, that is a simple example for 1D grid and 1D block. Okay, I'm not going to discuss 1D grid and 2D blocks and 1D grid and 3D blocks. Okay, you can easily interpret that. Okay, for the sake of simplicity, now I'm going to 2D grid and 2D blocks. Okay, 2D grid and 2D blocks. 2D, because if we know how to generate the global ID, remaining problems are pretty much simple. If you know the particular, then based on that, we can split the work. If you split the work, actually, we can get the answer for many applications. A 2D grid and 2D block. Yes. Remaining part of the program is same. Here, where is the logic? Logic is here, this one. Yeah, yeah. This is the simple piece of code. Here also, I'm going to call this compute using GPUs. When we look at the compute using GPUs, I'm going to call get global ID by using 2D grid and 2D block. This is the function call. By using this function call, when you look at this particular one here, what can you see? What is the meaning of the word 2D grid and 2D block? Yeah. First, I would like to give a simple overview on that. This is the grid. This is a grid. Now we have three blocks in x-axis and two blocks in y-axis and only one block in z-axis. In that context, this is a grid. In that context, dimensions of this particular grid is 3, 2, 1. Okay, three blocks in x-axis and two blocks in y-axis and one block in z-axis. Okay. After that, we are going to launch some number. This is for blocks, but threads in a block. See, when you look at the block threads in a block, what can you see? We can see that yeah. What is the configuration of this particular one? This is a block. Okay, configuration of this particular one is 5 threads in x-axis and 2 threads in y-axis and 1 thread in z-axis. Okay. Suppose if we launch this particular configuration, total number of threads is how many number of threads we are working with? How many number of threads? Per block, we have 10 threads, right? Number of threads per block is 10. How many number of blocks do we have? How many number of blocks do we have?
6 blocks,
6 blocks. So total number of threads
60
is
threads.
60. In that context, how do we get the unique thread ID? In that context, how do we get the unique thread ID? We have to use the coordinates of this particular block and coordinates of this particular grid. Grid is a collection of blocks, right? Okay, when you look at the coordinates, we don't bother about number of threads in z-axis. We have to bother about in 2D. We have to bother about number of blocks in x-axis and number of blocks in y-axis. When we look at this particular one, ID 0, 0, right? Are you with me? This is 1, 0. This is 2, 0. So for all these blocks, okay, block idx dot y, block idx dot y is 0. This is block idx dot y. Block idx dot y is 0. Are you with me? Next, for this particular block, all these blocks in this particular column, right, have same block idx dot x. What is block idx dot x value of this particular these two blocks is 0. Block idx of this these two threads are 1. Block idx of these two threads are 2. Are you with me? Okay. Now, suppose here our objective is we want to find a global ID of some thread which is there in this particular block, which is there in that particular block. How can we get that? How can we get that? Here our objective is we have to find the global ID of some thread which is there in this particular block. What is its coordinates of this particular block? Coordinates of this particular block, it is 1 comma 1 comma 1. Are you with me? Are you with me?
Yes, sir.
Okay. When it is 1 comma 1, okay. Okay. Simple calculation is, okay, how many blocks before this particular block? How many blocks before this particular block? 4 blocks. These are the blocks. Are you with me? Okay. After that, within the block, we have to calculate, we have to get that particular thread ID. Within the block, we have to get that particular thread ID. See, and first of all, here there is a logic to get the particular block number in a grid. Particular block number in a grid. Okay. When we look at this particular logic, here what is the value of block idx dot y? For this particular example, what is the block idx dot y? Here block idx dot y. What is the block idx dot y of this particular one? Any guess? Any guess? Block idx in y direction. Here, this is the block idx in x direction. This is the block idx in y direction. What is the block idx?
One,
What is that? It is
once,
1. Okay. Block idx dot y is 1. After that, grid dimension dot x. Okay. That means what grid dimension dot x means? Number of blocks in x axis. That means number of blocks in this particular row. How many number of blocks are there? 3, right? Times 3. Are you with me? Plus block idx dot x. Here, what is the block idx? That means within this particular row, how many blocks before that particular one? Within a given row, suppose when we consider this particular row, when we consider this particular row, how many blocks are there before this particular one? That is only one. That is this particular one, right? 1. So block number is, okay, how do we calculate? 1 times 3 plus 1, that is 4. 4. After that, this is the block number. This value is 4. After that, we are going to calculate, we are getting global ID with the help of this simple formula. What is this? Block dimension dot x. That means within a block, how many threads are there? In x-axis, we have 5. Block dimension dot y. How many are there? 2. Plus, here what is there? Here between these two, multiplication is there, right? 4 times 5, 5 times 2. After that, thread ID x dot y. Okay, that means within a block again. Within a block again there are multiple directions, right? Some number of threads in x-axis, some number of threads in y-axis, some number of threads in z-axis. Suppose within a block we are interested to find this particular thread ID, global ID, thread ID of this one. In the context, we have to consider a number of threads in x-axis, this one. After that, number of threads within this given row, number of threads before that particular thread. Okay. So with the help of this particular one, we'll get it. Okay. How many number of rows are there? Okay. Okay. Next one. And number of threads per row. Okay. Here, what do we get? Thread ID x dot y. Okay. That is the row index. That is the row index within a block. Okay. After that, when we use this particular formula, block dimension dot x, that means number of threads in the block in x direction. That is block dimension dot x. Here, when we consider this particular example, okay, for this particular one, uh, thread ID x dot y. Thread ID x dot y is 1 times. Here, block dimension is in x-axis, it is 5 plus. Here, after that, what is there? Thread ID x dot x. That is there. This is thread ID x dot x. Okay. What is the value here? Its value is in x direction 0, 1, 2. 1, 2. In that way, we have to calculate. Okay. Suppose when we use this particular one, what is the answer? Answer is 4 times 5, 20 times 2, 40, 40 plus 5, 45, 45 plus 2, 47, 47. We can easily verify this particular answer, whether it is correct or not. Okay. We suppose calculate. This one, each block we have 10 threads. This block we have 10. This block we have 10. This block we have 10. So 30. This block we have one more 10. That is 40. After that, this row we have 45. Okay. This is this 5. After that, number of threads before this particular one. Okay. That is this one. So this particular thread ID of this particular, okay, this particular thread of this particular block is, the global ID is 47. Are you with me? Are you with me? That is simple matrix operations, right? Do you have any doubt here to clarify your doubt? Okay. So suppose if you want to write efficient programs by using GPUs, okay, you should have some idea on how to calculate the global thread ID. Okay, based on that only we can write it. Otherwise, actually, we can write some programs by using GPUs. If you want to write the efficient programs, definitely when one should have some idea on how to calculate the global thread ID. Do you have any doubt or can I go ahead? Please let me know. This is the formula.
Fine, sir. Okay.
Fine. Okay. Now, what I'm going to do is I'm going to execute this particular one. NVCC minus O, a 2D grid, 2D block dot O. 2D grid, 2D block dot O. Yes, successfully compiled. 2D grid, 2D block dot O. Here, array size is 100. After that, yeah, I'm going to give the grid dimensions. 4 blocks in x-axis and 5 blocks in y-axis. Only one in z-axis. After that, uh, what can I say? I can say that three three threads in x-axis. Next one is five threads, not five. Actually, I would like to give three threads in y-axis and one is in z-axis. Okay, here grid dimensions are 4, 5, 1 and block dimensions 3, 3, 1. Instead of that, you can give the different answer, different. That is 4, 2, 1. So in that context, actually thread IDs varies from 4 5s are 20, 28s are 160. So this array is insufficient. Instead of 100, I would like to give 200. Yeah, now you can see. Now you can see. Okay. Total number of threads is 4 times 5, that is 20. 20 times 8, 160. So thread ID is from 0 to 159. 0 to 159. Are you with me? In that way, we have to generate the global thread IDs. Okay. Yeah. Now I would like to modify this particular program a bit. Okay. What I'm going to do is I want to generate only block ID. How can I generate the block ID? I'm going to add a formula here that is block dimension dot x times block dimension dot y. I'm going to multiply this one. Block dimension dot x. That means number of threads in that particular x direction times block dimension dot y. I'm going to divide this particular quantity with this particular one. In that context, what is the expected answer? Yeah. Did you find this particular one? Here difference is these are the threads of one block, right? Okay, when you look at this one, how many threads are there per block? 8, right? How many zeros are here? 1, 2, 3, 4, 5, 6, 7, 8. This is for this is from block 1. This is from block 2 and so on. Are you with me? Total number of blocks is 20. Let us see. This is 19. Okay. Here, when you look at this particular one, how many number of blocks are there? 20 blocks are there.
20.
How those 20 blocks are arranged? By using 4 rows and 5 columns. Are you with me?
Yes, sir.
Yes. Okay. This is a 2D grid and 2D block. Okay. Similarly, we can write the formula for 3D grid and 3D block. 3D grid and 3D block. Okay. Consider that particular one an exercise. You can try on your own. Do you have any doubt? I would like to discuss that one in the next class. Okay. Now take a break of for a period of 15 minutes. Okay. After that, by using this particular configuration, okay, I would like to explain two problems. That is, first one is dot product of two vectors. Okay. Second one is matrix multiplication. Matrix multiplication. Okay. Simple matrix multiplication by using CUDAs. After that, I'm going to give some parameters, configuration parameters, okay, based on this particular 2D grid and 2D block, okay. We are going to multiply those two matrices by with the help of those parameters. And let us see. Okay, okay. Then most probably after the break, I would like to discuss dot product of two vectors and matrix multiplication by using CUDA. Do you have any doubts? I hope that you don't have any doubts, right? Okay. Uh, Okay.
Yes,
Welcome
sir.
back to the session. Now I would like to discuss dot product of two vectors. Are you able to see the screen, right?
Yes, sir.
Okay. Do you know the logic for the dot product? Okay. I think there is no need to discuss dot product of this. Yeah. If you look at this particular dot product, usually for a simple problem, you know how to find the dot product of two vectors. If there is one vector, one, v1, quantities are one, 1, 1, and there is another vector v2. Those values are 1, 2, 3, 4. Okay. To find the dot product, what we have to do? We have to multiply these two values. 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 Later, we have to sum it up. Okay. When we find the dot product of these two vectors, its value is 10. Okay. Now, here our objective is we want to find the dot product of two vectors of two vectors. Okay, size of each vector is 10 power 9. That is very huge vectors, right? 10 power 9 is very big vector. In that context, we can solve that particular problem by using GPU programming or CUDA. We solve it. Okay. Here, this is the logic is very simple. The amount of work is we have to perform 10 power 9 multiplications. Okay, then we'll get 10 power 9 partial products. Later, we have to add all those partial products. Actually, then we will get final answer. Okay. Now we are going to, so this is the problem. This is the size of the problem. We are going to solve this particular problem by using 1000 CUDA threads or 1000 CUDA cores. Okay. In that context, how much amount of work we have to give to each core? In that context, how much amount of work we can give to each core? Simple thumb rule is this is the problem size. We are going to divide that particular problem size with the number of cores. Here, number of cores is 1000. So, amount of work given to each core is 10 power 6. That means each core is responsible to find the uh, a partial product of 10 power 6 quantities. Okay. So after that, what we have to do? We have to add all these quantities. Then we'll get the final dot product. Then we'll get the final dot product. Are you with me? Are you with
Yes,
me?
sir. Yes, sir.
Okay. In that context, how can we divide this particular entire work? How can we divide this entire work? Okay. So this is one vector. This is one vector. This is another vector. Okay. Now we have this is 10 power 6. This is also 10. Size of this one is 10 power 6. Size of this one is 10 power 6. And so on. This is 10 power 6, 10 power 6, and 10 power 6. Okay. We can launch one CUDA thread. That particular CUDA thread is responsible to find the dot product of these two subvectors. We're going to launch another dot product to find the dot product of these two subvectors. We're going to launch one more thread that is the dot product of these two vectors. This is one way, right? There are many ways to realize this particular logic. This is one of the ways. Okay. How can we do that? How can we do that? Okay. In that context, we have to find the boundaries for each thread. How can we calculate the boundaries for each thread? Suppose if this particular problem, what is the start index and end index of this particular thread? How can we calculate this particular start index and end index? Here, start index is 0 and end index of this particular one is 10 power 6
Or
minus
6
1.
minus 1.
Minus 1. Okay. Suppose if we consider 10 power 6, then we have to write the for loop logic is less than 10 power 6. I equal to 0. Okay. I less than 10 power 6. Then loop goes to 0 to 10 power 6 minus 1. Are you with me? Is there any difficulty? This is very simple and
Yes, sir.
straightforward. Okay. Similarly, for the next thread, what is the start index of next thread? For this particular thread, start
10 power
index
6.
is 10 power 6 to 2
10
times
power
10
12
power
minus
6.
1.
2 power 10 power 6 minus 1. If we use the similar logic, then we have to write 10 power 6, I equal to 10
Mm,
power 6, I less than 2 times 10 power 6. That's it. Okay, then loop goes to 10 power 6 to 10 power 2 times 10 power 6 minus 1. Just like that. If you build such kind of logic, we can do that dot product of two vectors. Okay, that is the logic. How can we do that? Okay, based on that logic, I'm going to explain the dot product. Yeah. Here I considered three arrays. Okay, don't work. We don't need this particular one. This particular. There is A, B. These are the two vectors and the host machine. These are the two vectors host machine. Okay, to find the dot product of these two vectors, what can we do? We can copy these two vectors from the host device. So we have to copy all the values of this particular vector A into DA and all the values for vector B into DB. So by using which function calls we can compute that particular one? CUDA memcopy. By using CUDA memcopy, okay, we can copy the data uh, from host to device or device to host. Okay. CUDA memcopy takes the four arguments. What are those arguments? Destination, source, and how much amount of data we are going to copy and direction of the copy. These are the four parameters. With the help of that, we can transfer the data between host and device. Next, after that, when you look at this particular thing, what can you see here? Here, I'm going to consider three parameters. Okay. Yeah, these parameters I will discuss at the end. First one is the size. This is the size of the vector. Second one is I'm going to solve this particular problem by considering some number of blocks and some number of threads. Okay. That number of blocks gives the grid dimension, grids, right? Usually in grid, we'll get the blocks in number of blocks in X direction, some number of blocks in Y direction, number of blocks in Z direction. After that, threads. Threads gives the, actually in threads also three-dimensional model. We can launch some number of threads in X, some number of threads in Y, and some number of threads in Z direction. Okay. Uh, that is the, suppose if without using dim3 data type, if we give it, we can give in one go, number of blocks in X, a number of blocks and number of threads per block. That is the configuration parameters. After that, okay, here what can you see? Here we can see that we are using the method CUDA set device 1. Okay, if you want, you can use actually here we don't need this particular CUDA set device. Okay. I'm going to comment this particular one. Anyhow, actually, we are accessing some particular one. By default, we'll get that particular device. Suppose if our server, okay, DJX server is going to give more than one, okay, in that context, we can get the list of devices. From that particular list, we can select the appropriate device for our needs. Right. Here, when we look at this particular one, there is alloc memory. This is used to allocate the memory on the host machine. This one is read array means these two function calls. With the help of these two function calls, we can initialize those two vectors. Where are those two functions? When we look at this particular logic, where are those two functions? Here you can see that. Here you can see those two functions. This is alloc memory. Alloc memory. With the help of this particular function call, we can allocate the memory on the host machine. After that read array, we are going to initialize both the vectors with 1. Reason behind that is if the both the vectors are with all the values of the vectors with 1, we can easily cross-check the answer. Okay, that is the reason. Okay, next one. Suppose if all the values on a particular vector are initialized with 1, what is the dot product? Dot product is the size of that particular vector. In that way, we can easily verify the answer. Next one. Okay. After that, when we look at this particular one here, what can you see? This is allocating the memory, and this is for reading the vectors. Okay. Once we read the vectors, right? After that, what we have to do? Some data is with the host machine. We had to copy back that particular data. Like we had to copy not we had to copy that particular data from host to device. To copy the data from the host to device, we have to use CUDA malloc. CUDA malloc. This is CUDA malloc function. With the help of this particular one, we have to this A is available in DA and B is with the DB. This is we had copying back both the vectors into the DA and DB. Sorry. Okay. Uh, Sorry for the mistake. Here I did a simple mistake. That mistake is CUDA malloc. Okay. Uh, the purpose of CUDA malloc is the device. Okay. This is CUDA malloc. That is, we are going to allot the this much amount of memory on the device. Okay. How can we access that particular one? We can access that particular one with the help of this particular variable DA. Next one is we are going to allot this much amount of memory on the device. We can access that particular memory with the help of DB. Okay. Later, once we allot the memory with the help of CUDA malloc, what we have to do? Uh, copy the A into DA and B into DB with the help of CUDA memcopy. If you look at this particular CUDA memcopy function, it is going to take 4 arguments. First one is the destination. Here DA is the destination and A. Second one is the source. Third one is amount of memory. Okay. This much amount of data we are going to copy it. And direction is host to device. Okay. Similarly, CUDA memcopy. After executing these two functions, now data is with the device. After executing these two functions, data is with the device. Are you with me? Do you have any problem? Is it clear? Did I create any confusion? Hi, please let me know. Did I create any confusion? Yes or no? Are you there?
Yes, sir.
Okay. If that is the case, okay, after that, I'm going to allocate the memory to store the result. I'm going to store the result in a dsum variable. Size of that particular dot product is a simple scalar value. That is why size of integer is sufficient. Next one. Okay. So once we executed these three steps, means that we copied both the vectors from the host to device. We copied both the vectors from host to device. Okay. And we allocated the memory to store the result, where the result is going to be stored in dsum variable. Result is going to be stored in dsum variable. Okay. Next, after that, after that, when you look at this particular one, I consider this particular one. I consider this particular one threads. Okay, this is simple program, right? Total number of threads is when we multiply number of blocks with number of threads per block, we will get the total number of threads. Suppose consider, okay, I'm going to launch 100 blocks and 10 threads per block. Then total number of threads is 1000. Suppose I'm going to launch 10 blocks and 100 threads per block. Then also total number of threads is 1000. Okay, based on that, we can split the work. Okay, that is a simple model to split the work among the threads. Okay, here based on that, calculate stride length. Stride length depends upon the size of the problem. If size, we are going to multiply two vectors of length 10 power 9. We are going to divide this vector with number of threads. Number of threads is 10 power 3. When we divide 10 power 9 with 10 power 3, in that context, stride length is 10 power 6. In that context, stride length is 10 power 6. Here I consider a simple formula n plus total length, total minus 1 by total. Okay. This is used to handle the corner cases. Here it is exactly divisible. Sometimes we cannot divide exactly, right? In that context, to handle those corner cases, this formula can be used to find the stride length. Okay. You can think about it. You can get the answer for that. Okay. Next, after that, here I use the get time of the day to measure the execution time of this particular multiply using GPUs. Okay. Usually, get time of day is not used to measure the execution time. But to measure the execution time on GPUs, we have to consider the events. Okay. For time being, we can consider this particular get time of the day. Reason is that actually here, I haven't considered any other functions at the same time. Here we have CUDA memcopy is there. CUDA memcopy is going to serialize the execution. Okay. That is a kind of CUDA memcopy has internal barrier. Okay. When we have during that scenarios, we can, with the help of this get time of the day before calling this particular one, after performing CUDA memcopy, we are going to execute get time of the day. More or less, we can get the approximate execution time. Okay. Let us assume that we'll get approximate execution time with the help of when we find the difference between TV4 and TV3. Okay, that is a simple program. When we look at this particular kernel function call here, what is the kernel function call? Multiply using GPUs. Here we are passing the two parameters. What are those parameters? First one is the number of blocks. Second one is number of threads per block. That is 1D grid and 1D block. That is straight away we are passing the number of blocks and number of threads per block. Okay. When we call, when our main program, okay, that main daemon thread calls that particular one, what is happening? It is going to execute. Okay, it is going to actually then CUDA is going to launch that many number of blocks and that's some number of threads per block and executes this particular method. If you look at the That is why we are calling this particular from the host. After that, for the given thread, start index and end index. Start index and end index. This is the formula to calculate the start index and end index. This is 1D formula, right? That's what I discussed while discussing this particular one. 1D grid and 1D block. Are you with me? Block ID x dot x times block dimension dot x plus thread ID x dot x. Did you remember that one? Okay. Idea is very simple. Suppose we have one dimensional block. This is one block. This is another block. This is another block. This is another block. And some number of threads in that block. Block ID x dot x. This block ID is 0. This is block ID is 1. This is block ID 2. Suppose we need the uh, start and end index of this particular thread. What do we get? First of all, we have to, with the help of this particular one, okay, what do we get it? This is block ID x dot x. This block ID x is 3. Means that number of blocks before this particular block. Number of blocks before this particular block is 3. In 1D case, with the help of this particular one, you can get that particular information. After that, block ID, block dimension dot x, that gives the number of threads per block in 1D model, 1D grid and 1D block. Suppose number of threads per block is 100. So number of threads before going to execute first thread of this particular block is 300. That is 300. After this, so this particular thread global ID is 300. After that, our objective is we have to find the global ID of this particular one, right? To get the global ID of that particular, then what we have to do within that block, we have to add thread ID x. Okay, now we'll get the thread ID, global ID of this particular thread. This is the formula. This is the formula to get the global thread ID. Once we know the global thread ID, yes, for each thread, we are going to allot some amount of stride length. We are going to calculate how much we are going to skip a certain part of the vector. We are from the remain. This means if there is a vector, right? If there is a vector, suppose this particular thread is responsible to work with this particular vector, this particular portion of the vector. Okay, then straight away with the help of this particular one, we straight away we can come to this particular point. Okay, this is the S index. This is the S index. Start ending it. After that, we have to identify the end index. How can we get the end index? We can get the end index this way. Okay. Yes. N index equal to S index plus stride length. Okay. With the help of that, we'll get the N index. Okay. After that, we are going to iterate between the start index and end index with the help of simple for loop. Where are we going to store the result? We are going to store the result in temporary variable. Are you with me? Are you with me? Are you with me? Now, suppose if you try to understand this particular logic, okay, up to till this particular point, suppose we are going to perform dot product of these two vectors with the help of 1000 threads, that is T0, T1, and so on. That means all these are the GPU threads. Okay, this is T9 999. Okay, this is in one temporary variable. This result is in temporary variable. This result is also in another temporary. Okay, this temporary variable is local to each thread. That is why this temporary variable is declared here. This temporary variable is declared here. This is local to each thread. Next one is we have to update all these sums into this dsum. Okay, this dsum is shared across the threads. When a value is shared across the threads, what we have to do? Okay, that update should be the atomic update, or we have to use some logs to perform that particular update operation. Are you with me? Or we have to use some logs to perform that particular update operation. Okay, that is why we considered atomic add. atomic add dsum comma temp. That means suppose if you are going to perform this particular update operation with the help of atomic add, okay, all these additions should be atomic additions. Then there is no data race problem. Otherwise, suppose if you write dsum equal to dsum plus temp, okay, in that context, uh, some of the threads updates may not be visible to the other threads. Reason behind that is actually because of data race. Because of data race. Okay. To overcome that particular problem, we have to consider atomic update operations. Okay. Yes. Now it is if all the threads executes this particular portion, this particular one, what will happen is result is with dsum. Result is with dsum. After that, what we have to do? We have to copy back that particular dsum to the host machine. Okay. Where we have to copy? We have to copy back that particular dsum to the sum. We have to copy back that particular result from dsum to sum. Once we copy back that result from dsum to sum, we are going to print that particular result on the screen. Are you with me? Are you with me?
Yes, sir.
Yeah. Here I wrote a simple function to calculate elapsed time. If we supply the two arguments, T3 and T4 are some arguments here, this function is going to give the difference between those two. Okay, difference in the execution time. With the help of that, we can call that. Okay, that is why here this is the function. This is the kernel. Kernel means function that is going to be executed on the GPU. With the help of this particular kernel, we are going to calculate dot product. Okay, after completion of this particular one, result is with the dsum. Later, we have to copy back that particular result into the sum. Result into the sum. To find the execution time, we are going to find the difference between uh, TV4 and TV3. When we find the difference between these two timestamps, okay, we'll get the execution time. Okay, this is the this statement device execution time. This statement is responsible to get the difference between TV3 and TV4. Are you with me? Are you with me? Can I execute
Yes,
this
sir.
program now?
Yes, sir.
Yeah. How can I verify the result? Suppose if sum equal to n, that means here I initialize both the vectors with 1, all the quantities with 1. Then dot product is equal to the length of the vector. Okay. Here length is n, so sum equal to n. Result is correct. Otherwise, there is a problem with that particular result. Okay. Next one is here. What can you see? Here we allotted the memory, right? So we have to free that particular one. Here, by how can we free the memory and the device? We can free it by using CUDA free function call. Okay. Suppose if we want to free the space on the host machine, how can we free it? By the help of simple free, right? Okay. Now, how can I execute this particular one? I can execute this particular one by using nvcc -o vector dot product dot o. Okay. I compiled it. What are the parameters here we have to pass? First parameter is, what is the first parameter? Size of the vector, right? Here I assume that size of the vector is 10 power 9. This is 10 power 9. And number of blocks is 10. Okay. Yeah, I'm going to solve this particular one with one block and one thread per block. If I use one block and one thread per block, definitely it's going to take more time, right? Let us see how much amount of time it is going to take. Okay, here it is going to take more time. Okay, I don't want to execute, spend that much time here. Instead of that, I would like to solve this particular one. 10 blocks with 10 threads, and that means that is 100 threads. 10 blocks and 10 threads per block. And then, yeah, here see, what is the execution time? This is total execution time. Don't worry about it. There is so much uh, uh, quantities are involved here. It is CPU memory allocation time and initial time is 8.8 seconds. And GPU memory allocation and initial, and that means we had to copy back that particular one from host to the GPU. That is 0.78 seconds. After that, actual device execution time. Device execution time is 0.59 seconds. 0.59 seconds. Okay, that is actual device execution time on the device. Now, instead of this particular one, 10 comma 10, I would like to solve this same problem. 10 blocks and 100 threads. 10 blocks and 100 threads. See the difference. Earlier, device execution time is 0.59 seconds. Now, the execution time on device is 0.15 seconds. Okay, we can solve that particular problem in less amount of time. Okay, when we look at this particular one here, we in our card is a A100 card, right? If it is A100 card, we can execute the same problem with at least 100 blocks and 100 threads per block. Okay. Then total number of how many threads we launched? We launched around 10,000.
10,000.
Yeah. See the difference. Here we solved the earlier problems. For this particular configuration, time is 0.15. Now it is 0.015. Okay, we got the 10x speed up, right? This is highly parallelizable application, right? For a highly parallelizable applications, if you solve it by using GPUs, we can quickly solve it. Okay. So which type of problem? Suppose matrix multiplication problem. That is highly parallelizable problem. Okay. We can solve by using GPUs. Suppose if you want to convert colored image to grayscale image. Okay. How can we convert color image to grayscale image? We can take the RGB values of each pixel and we can calculate the average of those three and we can convert that particular one into the appropriate grayscale value. Okay, such type of problems are highly parallelizable problems. We can solve such kind of problems by using GPUs in less amount of time. That is the beauty of it. Are you with me? Are you with me? Is there
Yes,
any
sir.
doubt in understanding this one, this example?
Sir, in A100 total 108
One we have
SMs, sir.
we have 108 SMs.
Yes, sir.
SM
Each
streaming
SM
multi
64.
each SM we can have 64 CUDA cores. Okay. Then total number of cores is 6912. When we multiply this particular one, we will get 6912. Right?
So this, okay.
Then
So
what will
this
happen is,
floating. Ah,
yeah, actually we are mapping here. How many threads we are launching? We are launching this many number of threads, right?
yes, sir.
Okay. When we launch that many number of threads, what will happen is, yes, actually, and each thread we are going to launch. So it is closer to 10,000, right?
Okay.
Suppose on average, each CUDA core is responsible to execute two threads.
Okay.
Can I say that? That means these two threads are going to be executed on that particular core in overlapped fashion, right? Suppose if there is a CPU, okay, this number of cores in your CPU is suppose 4 core mission or 8 core mission, right? On that particular one, we can launch some number of 16 software threads. We can execute or we can compute that particular task, okay, with the help of the 16 software threads, right? 16 software threads are mapped to the 8 hardware threads or 4 hardware threads, right? How are you going to map it? And they are going to map it in round robin fashion. That is simple round robin scheduling algorithm is there, right? Are you with
Yes, sir.
me?
Yes,
Yeah,
sir.
that is the case.
So it's
That is
a round robin fashion assignment only.
yeah. That is why here when we look at the number of physical cores is 6912.
Okay.
Okay, here number of software threads is 10,000, right?
Here also each core two thread or much
Yeah.
in
Actually,
CPU.
actually in this particular one, what is going to be happen is it is going to be executed in terms of warp, right? WARP, warp. You have idea. Warp is a group of threads. Okay.
Okay, okay.
In each iteration, how many 32 threads together it's going to execute it, right?
Yes, sir.
In each warp, okay, 32 threads are going to execute that particular task. That is why here also, in this particular problem, what are you going to do? For each thread, we are going to allocate the memory at one place, right? Okay, instead of that, we can distribute the memory in different ways, right? Instead of allocating the memory at one place, okay, yes, uh, one thread, okay, we can allocate the memory here. Next one, we can give the task to the another thread. For this one, we can give the task to another thread, right? Suppose if when we execute 32 threads together, if these 32 threads is going to access these memory locations, okay, then we can quickly solve the problem. Then we can quickly solve the problem. Yes, what can you do is you can perform different experiments on it. Anyhow, I'm going to share the code. Okay, what can you do is you have to perform different experiments on it. Okay, yes, while performing different experiments, do you have any problem? Please let me know. Otherwise, uh, you have to figure it out which one is the better model, okay, for your application. This is a very simple to find the dot product. Okay, this is the simple logic. How can we optimize this logic? Okay, what what are the action patterns of the threads in a warp? This is the action pattern of the threads within a warp. If this is the action pattern, how can we reduce the access latency? Okay, so to reduce the access latency, where should I place the data? Okay, in that way we have to think it and we have to find the optimized solution to solve this particular one. Are you with me?
Yes, sir.
Okay. Now, with that idea, now I would like to discuss logic for the matrix multiplication. Logic for the matrix multiplication. Are you with me? Suppose if I want to multiply two matrices, how can we do the matrix multiplication? Yeah, why matrix multiplication is highly parallelizable? Consider there are two matrices. One matrix of order 1000 cross 1000. One matrix of order 1000 cross 1000. Another matrix of order 1000 cross 1000. Another matrix of order 1000 cross 1000. How many multiplications do we need to perform to get the result? Okay. First one is number of elements in the resultant matrix. How many number of elements are there in the resultant matrix? We are going to multiply these two matrices, right? Each matrix of order 1000 plus 1000. How many number of elements are there in the resultant matrix? Order of the resultant matrix is 1000 plus 1000.
Thousands per thousand.
Then it is number of elements is 10 power 6. Okay. How do we get the each element? Number of elements is 10 power 6. To get the one element in the resultant matrix, we have to compute 10 power 3 multiplications. Why? Reason behind that is we have to take this particular row, we have to multiply with this particular column, right? Are you with me? So number of multiplications is 10 power 3. Number of elements is 10 power 6. So total number of multiplications is 10 power 9. Total number of multiplications is 10 power 9. Okay, in that way, so that is very And all those multiplications are independent of each other because this one and this one and this particular row with another row, this row with this row, all are that particular column, all are independent of each other. So this one is kind of massively parallel application, right? Similarly, addition of two matrices, okay, transpose of a matrix. All these are highly parallelizable, right? If those are highly parallelizable, we can do it by using GPUs. Okay. Okay. Addition and this transpose are very simple and straightforward. Okay. That is why I don't want to discuss addition and transpose. I want to discuss matrix multiplication. Okay. Here to multiply the two matrices, what can we do? Suppose if you want to multiply A and B, okay, we are going to take the row from matrix A and we are going to multiply that particular row with columns of matrix B. Okay, then we will get one row in the resultant matrix. Instead of considering the columns, okay, when we access this particular element, and after that we are going to access the next element. Okay, um, these two elements are a distinct apart, right? In that context, what can I say? If this element is at one memory location, definitely this element is at some other memory location, right? If these elements are contiguous in memory, then we can quickly access those elements. Okay. In that context, what can be done? Okay, instead of we can consider we can multiply A with B transpose. If we multiply A with B transpose, in that context, what we instead of multiplying row with row, okay, here we can get this A times B by multiplying A with B transpose. Okay, in that context, what kind of multiplications we have to do? We have to instead of we are going to take a row from matrix A and row from matrix B. Instead of taking a column, we are going to be taking the row. If we multiply these two rows, we will get the one element in the resultant matrix. Are you with me? Why? Reason behind that is here we are considering the B transpose. Okay. Yeah, I think I created a confusion, right? Confusion is no confusion. Actually, to for simple matrix multiplication, what are we going to do? Okay, this is matrix A. This is matrix B. Matrix B. Okay, we are taking a row from for matrix A and taking a column from B. Then we'll get a one element in the resultant matrix. Okay. Suppose to get the same element, what can we do? Okay, we can take the matrix A and we can here instead of B, we can take the matrix B transpose. Then we can take this particular row and take B transpose means this particular column becomes the row in transpose, right? Then we are going to take both. When we are multiply these two rows, we'll get the one element in the resultant matrix. Are you with me?
Yes, sir.
Yeah. I would like to explain that particular matrix multiplication logic with the help of that particular exam and this logic with the help of this particular logic. Then it is you can easily do it. Okay. See, Vi. Yeah, this is simple matrix multiplication logic. Yeah, similar to the previous one. Similar to the previous one, here also I considered three one-dimensional arrays. Okay. Yeah. When we look at the system's memory point of view, we don't find that much difference. All are contiguous in nature. All are contiguous in nature. We can matrix also we can consider as a simple one-dimensional array, right? Okay. Hey, what happened here? Okay. Now I can access it. Are you with me? Are you with me?
Yes, sir. Yes.
Okay. Yeah. We are going to multiply these two matrices. We want to multiply these two matrices. Okay. How are you going to multiply those two matrices? Is actually we are going to multiply these two matrix multiplication by using a device, by using GPU card. So for that, what are we going to do? Into DA, matrix B into DB. Okay. After that, we are storing the result in DC. Once we done the multiplication, we had to copy back that particular result to the C. We had to copy back that particular result to matrix C, and we are going to print that particular one. Okay. Is it clear? That is the little bit as an assumption. Here, A and B are the input matrices. C is used to store the result. Next one, allot the memory. Suppose to allot the memory, we can use uh, this allot memory function. N is the size, and where A is this X is the base address. Once we allot the memory, we are going to return a particular base address. Next one is read matrix. Actually, for the sake of simplicity, I initialized all the elements with 2. Okay. So in that context, okay, here I would like to give you an example. Here, matrix of order 1000 cross 1000. I am going to multiply two matrices of order 1000 cross 1000. Okay. If and all the elements of these matrices are 2, initialized with 2. In that context, what are the values of the resultant matrix? What are the values? We are going to multiply the corresponding elements. We are going to multiply 2 with the 2, 4. How many such type of multiplications we need to perform in 1000 cross 1000? We have to multiply that one with 1000 times, right? That means 4 times 1000, that is 4000. In that way, we can simply verify it. So to simply verify that particular result, 4 times n. If all the cell values, okay, not each cell value is 4 times n, then we can quickly verify the result. If program is correct, otherwise then there is a problem with our. Okay. Next, this is the logic to find the transpose. Anyhow, you know the logic for the transpose. Okay. Yeah. Here, look at this particular one. I'm going to consider this one is first argument is the rows, second argument is the columns. Okay. Let us assume that number of rows and columns for each matrix is same. Okay. Rows are same. Okay. Then you can quickly verify the result. Next to this third argument is the number of blocks, and fourth argument is number of threads per block. Number of threads per block. Suppose if I multiply rows with columns, if I multiply rows with columns, then what we get? I will get the number of elements per matrix. Number of elements in a matrix. Based on that, I'm going to allot the memory. Allot memory n comma a, and allot memory n comma b, and allot memory n comma c. Let us assume that we are working with square matrices. Okay. After that, by using this particular one, read matrix, okay, of A, read matrix of B. That means we are reading the matrices A and B. Later, with the help of this particular function call, I'm going to find the transpose. That means this is responsible to find the B transpose. Okay. Okay, after executing these steps, okay, till now what we did, we allotted the memory for A and B. Okay, we read the values into A and B. We calculate the transpose. We calculate the transpose. Transpose, where is the transpose? Transpose in B itself. Okay, we calculate the transpose. That is the assumption. After that, what we have to do? We had to compute this particular dot product. We had to compute this particular matrix multiplication by using GPUs. So we had to allot the memory, the device. To allot the memory on the device, CUDA malloc. CUDA malloc DA. That means we are allocating the memory for matrix A. Here we are allocating the memory for matrix B. After that, we are going to allocate the memory for matrix B. With the help of these three function calls, we can allot the memory for these three matrices A, B, and C. Once we allot the memory on the these three matrices, what we have to do? We have to copy the result, right? Okay, not copy the result. We have to copy the input matrices. We have to copy from host to device, A to DA and B to DB. Once we copy these two matrices from host to device, we have to execute that particular matrix multiplication logic by using this particular kernel. Here, what is kernel name? Kernel name is matrix multiplication using GPUs. Number of blocks and number of threads per block. This is the configuration parameters. Okay. With the help of these configuration parameters, we are performing this matrix multiplication. Okay. Once we perform the matrix multiplication, what we have to do? We have to copy back that result from the DC to C. C is on the host machine. C is on the host machine. Okay. Then we find the difference between these two. Get time of the day TV1 and get time of the day TV2. Okay, we will get the total execution time. Here we have to consider time for copying also, right? Suppose when we use the host mission, there is no need to copy, no need to perform the copy operation. Here we are considering device. In that context, we have to consider that particular copy operation also, a time for that particular copy operation. Is it clear? Is there any doubt? Are you with me? Are you with me?
Yes, sir.
Yeah. After that, here what I'm going to do is once we copy back the result from DC to C, uh, this is time to measure the this for elapsed time. Okay. Next one, this is the logic to verify the result. Okay. Each element in the resultant matrix is 4 times columns. Okay. Or 4 times n. There is no problem. Other than that, then there is a flag equal to 1 break. And that means there is a problem with our matrix multiplication. Okay. If flag equal to 1, fail. Fail means we are unable to perform proper matrix multiplication due to some reason, right? Pass means there is no problem at all. It gives the correct result. After that, we are going to free the memory space with the help of CUDA free DA, CUDA free DB, CUDA free RAM, free A, and post mission with the help of simple free function call. Okay. Now, actually, now I explained about this particular main function. What we have to do is we have to understand the logic of matrix multiplication using GPUs, this particular kernel. What is the logic here? We are passing the five arguments. What are those arguments? DA, DB, DC, and rows and columns. Rows and columns. Okay. If it is a square matrix, if we pass one value, that is sufficient. There is no need to pass two. Let us assume that I consider the rows and columns. For better understanding, you can do that. Okay. This is this particular simple matrix multiplication by using 1D grid and 1D block. That is why 1D grid and 1D block. Okay, you know how to calculate global ID by for 1D grid and 1D block. This is the logic to get the global ID. I already discussed. I spent sufficient time on it. Okay, next one. After that, what we have to multiply. We have to multiply particular row, this is a row of first matrix, that is matrix A. This is a row of matrix B. We have to multiply these two and we'll get the one element, right? If you multiply, row is same, and we instead of first row in the second matrix, if we consider this as second row, then we'll get the next element. If we consider the same row, that means first row in the first matrix and third row in the second matrix, then we'll get the third element, right? And so on. Okay. For that, this is the logic. Okay. Here, what we have to do is let us look at this particular one. Okay. Here we considered three for loops. Okay. For matrix multiplication, we need three for loops. Here, what the logic sees? I value is global thread ID. I less than the rows, and I equal to I plus total threads. That means, okay, suppose if we are working with, uh, we are going to multiply two matrices of order 1000 cross 1000, 1000 cross 1000, okay? And total number of threads is 100 blocks, and number of blocks is 100, and 10 thread plus block. I am going to launch 1000 threads. In that context, one thread is responsible for this one thread is another one, and so on, 9,999. Okay, in that context, what is the meaning of that? So in the resultant, suppose if this is the resultant matrix, this thread 0 is responsible to get one row in the resultant matrix. This one is responsible to get another row in the resultant matrix. This one is responsible next row in the resultant matrix, and so on. Okay, are you with me? All these particular results can be computed in parallel. Okay, that is why when we look at this particular logic, what can you see? I is the I value, we can get it from here. This is the global ID. I less than the rows. Okay, so row value. Next, I equal to I plus total number of threads. Okay, this is for simple nav implementation of matrix multiplication. Later we can think about the refined implementation, right? Okay, initially there is don't bother about that particular one. Okay. Anyhow, while sharing these programs, I will share both. I will share this naive implementation and refined implementation. What you have to do is you have to understand the refined implementation by using 2D grid and 2D blocks. Next one is here when we look at this particular one, each thread is responsible to access this particular one. J equal to 0, J less than N. Okay. J equal to J plus 1. Okay. Next one. Suppose after that, what we have to do for each, we are going to identify row and column, right? That means row in the second matrix. Okay. That the reason behind that is for second one, we found the transpose. Okay. We are going to calculate, okay, BFMR. Okay. But the purpose of that particular BFMR is base address of, okay. And this one is okay, BSMR. BSMR of is a base address of a second matrix row. Okay. For base address for the first matrix row and base address for the second matrix row. How can we get it? Okay, we can get it with the help of these two simple formulas. I equal to, okay, this BFMR equal to I star columns. Okay, what is I value? I value is the row index, right? Are you with me? Are you with me? Are you with me? I
Yes, sir.
values are the row index of the first matrix and J values are also row index of the second matrix. Okay. With the help of those row indices, we can get that particular corresponding base addresses, right? How can we get it? Actually, here, simple thing is, here we are going to use that the BFMR, okay, I star columns plus K. That here I would like to give a simple example here. Okay. This is first one. if k value is 0. If k value equal to 1, then we are going to consider next element. If k value equal to 2, then we are going to consider next element. If k value is 3, we are going to consider next element. Are you with me? Okay. Similarly, suppose BSMR, that means base address in the of second matrix, that is matrix row. Suppose consider this is the base address. This is the, we are going to multiply this one with this one. Next one is, as we increase the k, then what are you going to do is we are going to multiply this one with this one. Then we are going to multiply this one with this one and so on. Okay, that is the logic. This for loop is meant for that one. Okay, if you pick this particular row and pick one more row in the second matrix, we are going to multiply these two rows and storing the result in temp. Storing the result in temp. After that, we have to copy back. That means we have to copy that particular result. That means into the uh, final matrix. That is C. GC is used to store the result. GC is to store the result. Are you with me? Are you with me? This is a little bit
Yes,
tricky
sir.
logic. Please carefully go through it. Yeah. Here, BFMR. B stands for base. Base for the first matrix row, or first matrix. Okay. That means we are multiplying rows with rows, right? Because second matrix is in transpose, right? So we need the base at how can we get that particular index, right? I star columns, right? What is the I value? I value is the row number, right? Are you with me? Did you get my point? Right here, we have to
Yes, sir.
take this particular row. We have to take this particular row. We have to multiply with all the rows. This row, this row, this row, this row. Okay. When we multiply this row with all these rows, what do we get? We will get one row in the resultant
One row in the
matrix.
resulting. Yes.
One row in the resultant matrix. Okay. How can we get that? Actually, first one is actually to get that particular one. What are you going to do? We are going to take this particular one. Okay. This one is fixed. Okay. Once it enters into the loop, okay, this where is this loop control? This loop control is here. I value is depends upon outer for loop, right? This value. Otherwise, if you want to write this particular one outside this particular for this for inner for loop, you can write it. Don't worry. Okay. After that, this one varies with the j value. Initially, j value equal to 0, then we will get this particular row. If j value equal to 1, then we'll get this particular one. If j value equal to 2, then we'll get this particular one, and so on. After that, we are going to iterate this way. This is one vector. This is another vector. We are going to find the dot product of those two vectors. This is the dot product of those two vectors. That is simple scalar value. This is the simple scalar value. Where is that scalar value? That scalar value is a temporary variable. Later, what we had to do? We had to copy back that particular result. Are you with me?
Yes, sir.
Yeah. Now we are going to execute this particular one. Yes, to execute this particular one, what I have to do is, oh, and I'm unable to get that particular one due to some reason. The reason. Yeah, due to some reason, I was unable to connect it. I'm unable to connect it to the server. Okay. Anyhow, I will share that particular code with you. Okay. What can you do is you can execute that particular one with in your server. You will get some answer, right? Otherwise, I will show that particular execution in the next class, right? Is that fine?
Fine, sir.
Okay. Yeah, yeah. No, just a minute. Yeah, good. ZX. We're discussing about this matrix multiplication logic, right? Are you with me? NVCC minus O matrix multiplication dot O matrix multiplication dot O. What are the rows and columns? We are going to multiply two matrices of order 2000 cross 2000 by using 10 blocks and 100 threads per block. Yeah, we can solve that particular problem in 0.49 seconds, right? Instead of that, we are going to consider 100 blocks, okay, and 100 threads per block. We can solve that particular one in 0.27 seconds. Are you with me? In that way, here you can
Yes.
see that result pass. Pass means actually we got the correct result. We got the correct result. You want actually here in the code, I provided the different functions. If you look at that particular code, you can understand that. Suppose if you want to print the result, right? If you remove that particular comment here, you can see that I put the comment print text, print matrix, right? If you remove that particular comment, you can print that result on the screen. Okay, you cannot print the result of 1000 cross 1000. Instead of that, you can print the result of two matrices, 10 cross 10 or something, right? Now I'd like to show the execution for small matrices. I multi-execute it one more time. Instead of this one, I'm going to multiply two matrices of order 15 cross 15 by using four blocks and four threads per block. That is 60. Are you with me? This is the
Yes,
result.
sir.
Okay. That's it. Do you have any doubts?